Hello everyone, in this video we're going to be counting in binary. So you can see on our board we have a list of numbers from 0 to 12 in our normal format that we're used to dealing with, which is decimal. So we're going to convert these numbers from 0 to 12 into their equivalent binary numbers, and to do so we're going to use our powers of 2 table to help us out. So to start off with our powers of 2 table, we're going to go 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3. And we're only going up to 2 to the power of 3 this time because that's all we need for this video. So 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, and 2 to the power of 3 is 8. And the reason why we're only going up to 2 to the power of 3 is because if we have a number like 1, 1, 1, 1, this is the highest number that we can represent just using our 4 digits, or 4 bytes we can call them. So this binary number here is actually equivalent to 15, and the reason why is because if we add 8, 4, 2 and 1 together, we'll get 15. So 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. So this table can help us out as we're going through our binary numbers. I want to mention something quickly that we've went over in previous videos a little bit, and I just mentioned it there a second ago, is the fact of having a bit. So when we had our 4 ones here, I said that these were 4 digits, or another name we can refer to them as 4 bits. So a bit can be either a 0 or a 1. So you'll see as we're going through these numbers, for these numbers we might be converting it into a binary number. Now some of the binary numbers may require just 1 digit to represent it, like 0 or 1. Some other numbers might require 2 digits or 2 bits, like 2 and 3, and then some other ones will require 4 bits, like 12 and 11 and 10. So just keep that in mind. So as we all know in binary, binary is 1 and 0. So we can represent both the numbers 0 and 1 in decimal and in binary. So when we're converting from 0 from decimal to binary, it's going to be the same. It's going to just be represented as a 0. And the same goes for 1. If we have 1 in decimal, it's also represented as 1 in binary. Now this is where things start to change a little bit. It's when we get to the value of 2 and 3 and 4 and so on. So when we get to the value of 2, normally we represent it like this, but in binary it's represented like this, 1, 0. And I'll tell you how we come about this. So if we have, let's say, 1 and we have another 1, and we want to add these together, right? So if we were to add these together normally, we would add 1 and 1, which would give us 2. But with binary we can't really do this. That's because we can't represent the number 2. So what we have to do is we have to bring our 1, we have to carry, and we can carry 2. So we've got 2 here, so we can carry our 2 to the next column, and this will be 1. And once we've carried it, we can then put down a 0 here. And then we bring down the 1 and it's represented like this. In the next coming videos we'll be going into more addition and subtraction in binary, so if you don't quite get this yet, don't worry about it. Now another way we can look at adding binary numbers or converting our decimal numbers to binary is by looking at our little table over here. So if we look at this and we can see that this number is 2, this number is 1, this number is 4, and this number is 8. If we have our number 2 in decimal, how could we make up the number 2 just by using these numbers? Well, we could just use the number 2 here. So we could say that we want one of those 2's, and we don't want anything else, so we can just fill in all the other places with 0. And that's what we do here. Now you could also put in 2 zeros here as well, indicating that you don't want 8 or you don't want 4. But for this example, we're just going to represent the numbers like this. So then when we move on to 3, let's say we have 1, 1 and 1, and we want to add these together. Now again, in decimal format we can just add these 3 together and get the number 3. The problem with binary is we can't even represent 2. So if we can't represent 2 in binary, we definitely can't represent the number 3. So again, we're going to have to carry on to the next column. So what we can do is, we've got 3 here, so to create the next column we need 2. So we can carry 1, so that's basically the same as saying we've got 3 here, we've taken 2 away, we've added to the next column, So if we've taken 2 away from 3, it's going to leave us with 1. So we can just put 1 down here, and then we're going to bring down this 1 also. So it's going to look like this. It's going to look like 1, 1. So we put this down here for 3. So if we want to go and figure this out using our table, we can think about what numbers here can we use to get 3. So we could use 1, 2 and 1, 1. So that would work. So 2 plus 1 is 3. So again, you see that we have 1, 1 here, which is the same answer we got doing it the other way. Now I'm going to let you run through the rest of them. I'm going to do them out for you so you can check your answers. So these are the rest of the answers, and if we want to go and pick one of these numbers just to double check it, so let's say for example we pick the number 9 and we want to make sure that this binary number is actually 9. So what we can do is we can go over here and we can write down the binary number that we think equals 9, so 1, 0, 0, 1. And what we can do is we can go and look at these numbers above, so we can say that, okay, this is the same as 8 multiplied by 1 plus, so there's no need to do 4 multiplied by 0 because that's just 0, 2 multiplied by 0, that's just 0, so there's no point in writing it down, and then we've got 1, so we can multiply 1 by 1, so 1 multiplied by 1, so 1 by 1 would be 1, then we're going to add 8 multiplied by 1, which is 8, and this gives us our answer as 9. So we can check our answers using this method. Now, one thing that I touched on earlier on in the video is this idea of our bits. So you can see now what I meant when I said 1 and 0 you are using 1 bit, and you can see the likes of 4 and 5 are using 3 bits, and 11 and 12 and 10 are using 4 bits. So this is not actually the way it's represented. So this isn't fully correct, because if we declare a variable and it only has maybe 2 bits in it, if we want to increase that number to a larger number that will need more than 2 bits, then we can't actually do it. So for example, if I create a variable, this syntax is going to be JavaScript, so let num equals 5. So that means that we can redefine the contents of this variable whenever we want. So num is the name of the variable and it's equivalent to 5. We've assigned 5 to this variable, so we can see from here our table shows that 5 is equivalent to 1, 0, 1. So this is our binary number. Now if we have a variable that just has 3 bits, because this is 3 bits, 1, 2, 3, and then we want to change our number from 5 to 10. So for example, let's say we're redefining our num, so we say num equals 10. Now the problem we have is we have a num that we've defined and it's able to hold 3 bits, but now we're trying to assign 10 to num. So if we look at 10 here, we can see that it has 4 bits, so there's just not enough space. So the way we get around this is by giving a variable loads of space when we initially define it. So while we've assigned this to 5 and 5 only needs 3 bits, we actually give the num variable 16 bits or 32 bits. So for this example, I'm going to use 16 bits. So some programming languages use 32 bits to hold their integers, some use 16 bits, and some give you an option of deciding on how many bits you want an integer to take up. For this example, I'm using 16 just because of space. So how this example would work is 101 is equivalent to 5. So on this line here, where we define our num as 5, we would have 1, 0, 1, and then all the rest of our numbers here would be 0. So it would look like this. Now, when we want to change from 5 to 10, we can just get rid of these 3 bits, and we need to change this 4th bit here, and we're going to change it to 1010 because 10 is equivalent to 1010 in binary. So we just put down 1010, and now we've changed our num variable from 5 to 10. And then we can also change this from 10 to maybe 105 or 1005 or 99 or whatever other number we want. Now you might be thinking, these bits here are all wasted. So, you know, if I'm only gonna count up to 15 or whatever, can I not just use 4 bits? Because if I know my number is never going to be greater than 15, can I not use 4 bits? You can in some programming languages, but you need to take into consideration in most cases you're not going to be sure what number the user is going to put in, or the maximum number that the user is going to put in. So you're going to want to have a margin of safety. So you're better off going with a much larger number and you're able to take in whatever the user puts in, rather than not being able to store whatever number the user gives you. So it's up to you as a programmer to decide what you want